Okay, so for our first warm-up here, we're asked to determine the x values for which x has extrema, is increasing and decreasing, and is concave up or concave down. Okay, so the function we have is that f of x equals the sine of x. Okay, and it's on the domain 0 is less than or equal to x is less than or equal to 2 pi. So what this means is because this is a closed interval, we're going to have to consider the endpoints as critical values, meaning they're most likely going to be minimums or maximums. Okay, so critical values would be endpoints wherever the first derivative is equal to 0 and also where it's undefined. If we have undefined points, those are also critical values. We haven't talked a lot about that yet. So the first thing we're going to do to find our critical values is we're going to go ahead and take the derivative. Right? So hopefully we all know that f prime of x would be the cosine of x. Okay. Now I heard people talking in terms of angles or degrees out there. We really don't want to do this in degrees at all. We need to work in radians. So that's a thing. But we know that between 0 and 2 pi, that the cosine, so we have 0 and we have 2 pi. I'm going to go ahead and exit out outside of that because we don't need that to happen. But if we think about when the cosine is equal to 0, I just think back to the unit circle. And on the unit circle, the cosine is the x value, correct? So x is equal to 0 up here at pi over 2 and down here at 3 pi over 2. So we're going to get pi over 2 and 3 pi over 2. Those are going to be, right, so in terms of critical values, we have 0, pi over 2, 3 pi over 2, and 2 pi. Okay, those are the ones we're going to have to consider here. So let's figure out what kind they are, and let's look at where this function cosine is positive and where it's negative. Now, in the first quadrant, between 0 and pi over 2, cosine is positive, right? Over here, in the second quadrant, it's negative, just like it is in the third quadrant, right? That's from pi over 2 to 3 pi over 2. And then it's positive from 3 pi over 2 to 2 pi. Now, I guess you could have done test values, but that seems kind of unnecessary if you just think about the unit circle, right? Or the, all students take calculus, right? So they're all positive, and the cosine's positive in the first and the fourth quadrant. This is first and the fourth quadrant. Okay, so now, in terms of our extrema, we're talking about our local mins and local maxes. We want to consider all 4 of these points. So with this, if we're at whatever point is on the original function sine at 0, we know that to the right of that it's going to be increasing, correct? So if we're at a point and we increase, if you're at the left end point and you increase, it would have to be a minimum. Right? So we have a minimum at x equals 0, and then the original function increases, and at pi over 2 it starts decreasing. So that's a maximum. So that would be x equals pi over 2, and we want this to alternate because it's a continuous function. Next up, we decrease until we get to 3 pi over 2 on the original function. Then it increases, or the first derivative is negative, then it becomes positive. Everyone look at that. So that's x is 3 pi over 2 would also be a local minimum. Right? And then the derivative is positive, or the original function is increasing until we get to that right endpoint at 2 pi. So it increases, stops. That means it would have to be a maximum. Okay, so here we have our extrema. Okay, I guess it asked about increasing and decreasing. Might have been easier to talk about that first. So in both of these, f has a local minimum. F has a local maximum. F is increasing from 0 to pi over 2 and from 3 pi over 2 to 2 pi. And then f is decreasing from pi over 2 to 3 pi over 2. Because the first derivative is negative, right? First derivative negative means f is decreasing there. First derivative positive means f is increasing there. So we have that. The next thing we're asked about is the concavity. Where is it concave up? Where is it concave down? Well, our first derivative is the cosine of x. So then our second derivative, what's the derivative of cosine of x? Negative sine of x. Okay, so if you think about the graph, it starts at the origin, but instead of going up first, it goes down first. What happens there? So, in terms of the number line for f double prime, we still have 0 and 2 pi on there because those are those endpoints of our closed interval. And then let's see, sine starts, it's at 0, the sine of 0, maybe draw a unit circle again. Sine is the y value, so sine is equal to 0, at pi, and at 2 pi. So, okay. Now, I know that sine is positive from 0 to pi because all students, right? It's positive in the first two quadrants. And then I know that between pi and 2 pi, it's negative. So, is that going to tell us about concavity? Sure. So we'd say f is concave up from 0 to pi. F is concave down from pi to 2 pi. We're going to leave those as open intervals. And then if you wanted to, we could say there's a point of inflection at pi. Yes?
So do you not even take the negative into account then when you're determining concavity?
Oh, no, I should definitely take it into account. So I did it backwards, didn't I? Yeah, no. Yeah, negative, kind of a big deal. I was all excited to use the unit circle. I'm sorry. So yeah, that would be like that. That was wrong. Yeah, I just had the wrong function. I did write the same thing. Well, at least I'm consistent, right? Okay, so I could do this. Concave down, concave up. How's that look? All right, so then we could say there's a point of inflection at x equals pi. Now, especially in light of that little goof up there, since we know actually what the sine of x actually looks like, it might be nice to compare the data that we collected from the first and second derivative to what the graph actually looks like. So here we get what, pi over 2, pi, 3 pi over 2, 2 pi. So here, so here's the original function, correct? So let's see if what we said was correct. Does it appear to have, oh, a local minimum? Sorry, I misread. Does this look like a local minimum? Sure. Does it have a local minimum at 3 pi over 2? Yes, it does. A local max here at pi over 2 and at 2 pi. It's an endpoint. So it is increasing from 0 to 2 pi, or pi over 2. It's increasing from 3 pi over 2 to 2 pi. It's decreasing on this interval. Is it concave down from 0 to pi? Seems pretty believable. Is it concave up from pi to 2 pi? Seems believable. It does have to change concavity. It makes sense that it would do it at the halfway point. Okay, so you good on that one? Yeah. All right, so for example here, we're going to look at a function that's not a polynomial. We just wrapped up a trig function. So determine the critical values, extrema, increasing, decreasing intervals, and the concavity of the function. So we're going to need to look at the first and second derivative. Okay, but before that, we should consider that since we do have a radical here, we have a domain issue. Right? So on this function, as it's written, the domain is that x is greater than or equal to negative 3/2, correct? Everybody, this has to be greater than or equal to 0. Solve it. X is greater than or equal to negative 3/2. So that means when we're looking for extrema, when we're looking for critical values, negative 3/2 is going to be one of those. Okay, so the next thing we do then is we're going to take the derivative. So here, recall we probably want to think of this as 2x plus 3 to the 1/2 power before we take the derivative. So then f prime of x would be 1/2 2x plus 3 to the negative 1/2 times 2. Don't forget the chain rule. I tend to forget the chain rule a lot, so be careful there. So we get f prime is, I mean, I could write it a lot of ways. I'm going to probably write it as 1 over the square root of 2x plus 3, right? I mean, that's as good a way as any to write that. So if I think about this, does this function have any zeros? No, it's never equal to 0, right? So the only critical value is this negative 3/2 right here. Okay, so our number line for f prime will have negative 3/2. Nothing happens to the left of it because the function's undefined. Right? And then as I look at this, if I plug in any number greater than negative 3/2, is f prime of x going to be positive or negative? Put in 0. So that would give me 1 over the square root of 3. Is that positive or negative? Positive. Well, good. It's kind of boring, right? I mean, so what's this tell us? This tells us that the critical values, well, there's only one, is that x equals negative 3/2. Okay. Is that going to be a minimum or a maximum? Because it's the left endpoint. From that endpoint, we increase. So it would be a local minimum. It actually might be the absolute minimum because there's only one. So we can say that we have a local minimum also at x equals negative 3/2. Now, are there any intervals on which it's decreasing? No. So we would say that f, and I guess we should say f has a local minimum. F is increasing on the interval from negative 3/2 to infinity. Okay. And because negative 3/2 is defined on the original function, we will still go ahead and use the bracket there. Okay. But it's actually not defined on this function. And if you investigate further, we'd see there's a vertical tangent on the original function at negative 3/2. But again, that's probably a little bit beyond the scope of what we're talking about right now. So we did that. So next step is to find the second derivative, right? So we have f prime of x. Probably easiest to look at this as 2x plus 3 to the negative 1/2, right? Does that work for everybody? And then we'll take its derivative. So f double prime of x will be negative 1/2, 2x plus 3 to the negative 3/2 times 2. Is that everybody with me there? So let's simplify that. F double prime of x, maybe negative 1 over the square root of 2x plus 3 cubed. Sometimes it's nice when you're actually analyzing the function to actually use the square roots. I think it makes it more clear. So, well, is this ever going to equal 0? No, because a constant divided by anything will never be 0. Do we still have a critical value? I still have to look at this endpoint. So then for f double prime, we have negative 3/2. To the left is nothing. But if we pick a number like 0 again, anything in this interval, or 1,000, whatever, anything over here, we'll see that we get a positive number on bottom after we square root it, right? And negative 1, a negative divided by a positive will be a negative. So that tells us that f is concave down from negative 3/2 to infinity. There's an underwhelming amount of information here. Like, it's just not a very interesting problem. But there you go. Any questions with that? Is there a point of inflection? No, because the concavity never changes. You might go back. We know the square root graphs just look like a half a parabola on its side, correct? So if you think about what the actual original function looks like, looks like that. Has a local min, which is actually the absolute minimum, if you were asked about that, and then it's concave down everywhere. That's it. So that's how we do that one. Okay, so for our second example here, we have a rational function, f of x equals x squared over x minus 2. So right away as we look at this, we see that we have a domain restriction that x cannot equal 2. So that means when we make our number line for f prime and for f double prime, we're going to have to include 2 on there, right? It won't be a min, it won't be a max because it's not defined, but the values of the function or the derivative function or the second derivative can change from positive to negative because there's a vertical asymptote there. You picked up your pencil. You got to figure out where you put it back down. So our first order of business here is to take the derivative. Okay, looking at this, this is a quotient rule, most likely. So I'm going to go ahead and say u is x squared, u prime is 2x, v is x minus 2, v prime would be 1. So then our f prime of x is going to be v times u prime minus u times v prime over v squared. So then at this point, we just need to simplify this numerator because we have this, we'll want to distribute the 2x, kind of clean it up. So f prime of x is 2x squared minus 4x minus x squared over x minus 2 squared. And then as we clean this up, write this up here, f prime of x is equal to x squared minus 4x over x minus 2 squared. Did we all get that for our derivative? Okay, now, to find our critical values, we know that 2 is going to be a critical value, but we also have to investigate when the numerator is equal to 0. Right? We know a fraction or a rational function or expression will only be equal to 0 when the numerator is 0. Right? It doesn't really matter what the denominator does. So let's see, x squared minus 4x equals 0. We could factor that out, and we're going to get that x equals 0 or x equals 4. So then our critical values are going to be 0, 2, and 4. So we're going to include those on our number line here. So let's see, we get a number line for f prime, 0, 2, and 4. And we just want to find whether it's positive or negative in those different intervals. So let's see here. We're going to test it against this function here, or maybe, well, is the denominator always going to be positive? It's squared, guaranteed. It's always positive. Doesn't matter what you put in. So I don't even have to look at it. So I could just think of I really could just test against x times x minus 4, which is just the numerator. Right? If the numerator is positive, it's positive. If the numerator is negative, it's negative. So here, let's test maybe negative 2, and we get a negative times a negative. So that would be positive. Here we could test 1, and that would be a positive times a negative, which is negative. Here we could test 3, which is a positive times a negative, which is still negative. Now we're not used to seeing two negatives next to each other, but remember, there's a vertical asymptote here, right? So that's why that happens. And then here we get x equals 5, which is a positive times a positive, which is positive. I could note here these were actually zeros, correct? Where 2 was not. 2 was the vertical asymptote, so you might even indicate that with an open circle, like, hey, that's not going to be part of any of my increasing or decreasing intervals because it's undefined on the original function, just as a kind of an idea there. So what we have here, these were our critical values. Let's see, f is increasing from negative infinity to 0 and from 4 to infinity. And then f is decreasing from 0 to 2 with the parenthesis union 2 to 4. So we do want to leave 2 out of there because it's undefined on the original function. We can't compare 2 points in there, the slope between them if it's not actually a point. And then let's see, what else do we have? We have so f has let's see, local max, see if it has one, a local min. Well, this tells us if it's decreasing as it approaches the vertical asymptote, it's just going to go down forever, right? There's no minimum there. And here to the right of it, if it's decreasing, must mean that it was up high there. Like this kind of shape up there that we're looking at there. But anyways, so here we went from increasing through 0 to decreasing. So at 0 there would be a min or max? Max, right? If f prime goes from positive to negative. So that would be at x equals 0. And then here we have it decreases, right? Or well, the original function decreases until it gets to 4, then it increases. Or the derivative goes from negative to positive, which means we have a min at x equals 4. We good there? Next up, we need to find the second derivative. Oh, good. That sounds fun. Let me just grab another board here to kind of help. So for the second derivative here, we have f prime of x is x squared minus 4x over x minus 2 squared. So let's just look at finding that derivative here. It's going to take a little bit of work. So we have that u is x squared minus 4x. So u prime is 2x minus 4. And then we have v is x minus 2 squared. So v prime would be 2x minus 2. Right? And then when you take the derivative of x minus 2, you just get 1. So that worked out okay. We good so far? And again, we're just trying to find the second derivative. This is the equivalent of working on the back of the piece of paper, I guess, copying it down. So for f double prime of x, we're going to do v times u prime. Really, that's kind of unpleasant. X minus 2 squared times 2x minus 4. And then minus x squared minus 4x times 2. I'm going to write, instead of 2 times x minus 2, maybe I just write it as 2x minus 4. That seems believable, right? And then on bottom, we'll get x minus 2 to the 4th. Right? We took something squared, we squared it to the 4th power. Alrighty then. Well, I promise this does simplify out pretty nicely.
Well, I called you right as you
Which is kind of surprising. Actually, I'm going to change course here. Let's leave this as 2x minus 2. Because now if we look, there is a common factor here that we could pull out, which will make it easier to distribute some stuff. Like we won't have to actually square and then multiply. So let's write this as f double prime of x. We'll pull out an x minus 2. We could have written this one also as 2x minus 2, couldn't we? This piece right here. Yeah, so then we can, and I don't know if that even helped any. Sorry, halfway through the problem here, I keep changing things, but we leave it like that. It's fine. So I'm going to pull out one of the x minus 2's. That's going to make it nicer. So this is left with x minus 2 times 2x minus 4 minus x squared minus 4x times 2, right, because I pulled out this x minus 2 and put it out here. And then on bottom, we have an x minus 2 to the 4th. So what we're going to see is this piece that we factored out can reduce with this piece on bottom, which will make things nicer. Okay, so again, not the easiest derivative we've done today. So that'll go away with one of these. So on bottom will be x minus 2 cubed. Here we need to go ahead and multiply these two together. So that's going to be 2x squared minus 4x plus 8. Then here we need to distribute the negative and distribute the 2. So let's do negative 2x squared plus 8x. Well then, luckily, 2x squared minus 2x squared cancels. Negative 8x plus 8x cancels. So we get that f double prime of x equals 8 over x minus 2 cubed. So we'll write that up here. So f double prime of x is 8 over x minus 2 cubed. So it's kind of nice when all that terrible work just, everything cancels, right? So now, to make our number line for f double prime, is this ever going to be equal to 0? No, but there's still a critical value at 2, correct? Because of the original, we push this back over here. There's still the critical value at 2, so for our second derivative number line, right, we're just going to test to the left of 2 and to the right of 2. Now, so if I put let's say I put 0 in here, it would be to the left, correct? So if I tested 0, well, 8 is obviously positive, but this would be negative 2 to the cubed, which would still be negative, right? The negative's preserved, so that's negative. Or here, if I tested, say, with 4, which is to the right of 2, you'd get 8 over, I guess 8, positive over positive, which is positive. Okay, so that tells us then that f is concave up from 2 to infinity. F is concave down from negative infinity to 2. Right? Negative, second derivative's negative. It's concave down on that interval. How, well, by definition, if f double prime, remember here that if f double prime is greater than 0, it's concave up. And if f double prime is less than 0, it's concave down. Now, do you think the original function, oh yeah, question?
Since 2 isn't in the domain, would it still be a point of inflection?
That was my next question. What do you guys think? Do you think that 2 would be a point of inflection? I think no. No, it's not. Because it's not in the original function. What we have here is a case where, if you want to think about it, for the graph, it probably, at 2, we have this vertical asymptote, right? And so I guess it's going to be concave up and then concave. It's probably looking something like this. It's kind of what we're dealing with here. So no, I think that we were not going to call that a point of inflection. I can ask smarter people than me and find out, but I would say no, that's not a point of inflection. I probably need to check the definition a little bit more. Are there any other questions here? So it makes you miss the days of polynomials, correct? Because this is not very much fun, so thank you.